What unfolded for 3I on September 7th, during the lunar eclipse, has irrevocably altered our comprehension of this visitor from beyond our solar system. The celestial body, which only a month prior astronomers had confirmed was emitting scarce diatomic carbon, has dramatically erupted in vibrant green luminescence, showcasing molecular signatures that spectroscopic analysis had indicated were absent. However, this is merely the prelude to a cascade of revelations that are actively redefining the very principles of cometary physics. While you were observing 3I Atlas's progression toward perihelion, the Hubble telescope unveiled an unprecedented phenomenon in astronomical history, a sunward expansion of scattered light, stretching 10 times the comet's width and pointed directly towards the sun, defying conventional understanding of radiation pressure physics. And here's what's fueling the news that is perplexing even seasoned space aficionados. The viral assertions regarding a second immense comet purportedly hurtling towards us are not indicative of a new discovery. They stem from a conflation of Bernard Donnelly Bernstein's unhurried approach with 3I Lass's current transit, creating a perfect storm of misinformation spreading with alarming speed, far outpacing the actual scientific findings. Tonight, we embark on an in-depth examination of the latest data that has surfaced just this week. You will learn why Atlas's cyanide production is escalating at rates that conform to a power law with an exponent of 9, a mathematical behavior suggesting a chemical composition unlike any observed in solar system comets. We will investigate how TESS observations revealed the comet was already exhibiting activity in March, when it was situated beyond Jupiter's orbit, activity that challenges our established understanding of volatile sublimation thresholds. Most importantly, you will grasp why Avi's analysis of the HPE imagery points to geometric corrections that render this sunward phenomenon even more pronounced than initially reported, and why this solitary observation may compel us to reevaluate fundamental assumptions about the behavior of interstellar objects when exposed to stellar radiation. The data anticipated from the Mars encounter in a mere 2 weeks will either corroborate that we are witnessing exotic physics or indicate that Atlas operates by principles yet to be discovered. But first, we must thoroughly comprehend what that emerald transformation elucidates about chemical processes that might be exclusive to materials forged around alien stars. Before we commence, I encourage you to engage the like and subscribe buttons, but only if you genuinely appreciate these scientific explorations designed to foster relaxation, focus, or sleep. You can also contribute to this video's reach through the new hype feature situated below. In the comments, please share your listening location, the local time, and the most peculiar scientific phenomenon that captivates your curiosity. I will be responding to many of your comments, and who knows, your suggestion might inspire our subsequent video. Now, returning to our vividly green, luminous visitor and the enigma that has captured global attention. The impossible emerald transformation. For months, every spectroscopic examination of Atlas presented a distinctly ruddy hue, consistent with expectations from ancient interstellar material. This coloration narrated a tale of primordial compounds, perhaps unaltered for billions of years as this cosmic time capsule journeyed through the void between stellar bodies. Then, on September 7th, during the lunar eclipse that shrouded our skies, a shift occurred. Yerger and Raymond's photographic evidence showcased an undeniable emerald radiance emanating from our interstellar guest. This was not a subtle change, nor a processing artifact or atmospheric illusion. The metamorphosis from red to green signifies a fundamental alteration in the chemical reactions within Atlas's coma, the luminous envelope of gas and dust encircling its nucleus. Harvard's Avi Loeb, whose unconventional theories concerning interstellar objects have ignited both fascination and debate, immediately recognized the significance. The green luminosity in comets is typically attributed to diatomic carbon molecules, carbon atoms joined in pairs that fluoresce under solar radiation. However, this is where the enigma deepens beyond readily acceptable explanations. Merely 1 month prior, astronomers at Kitt Peak Observatory had specifically sought carbon chain molecules, including diatomic carbon, within Atlas's spectral signature. They detected virtually none. The scarcity was so striking that it effectively excluded diatomic carbon as a significant constituent of the comet's makeup. Yet now, mere weeks later, the object is glowing green with what appears to be the unmistakable imprint of those very same molecules. What precipitated this change? Several hypotheses emerge from the fringes of our current understanding. Perhaps the sun's intensifying heat has penetrated deeper strata of the comet's nucleus, releasing previously concealed reserves of carbon compounds locked beneath the surface. Perhaps we are observing the initiation of chemical processes that do not occur in comets native to our solar system, reactions that only manifest under the specific conditions presented by this alien visitor. Or perhaps, as some researchers cautiously propose, the green radiance originates not from diatomic carbon, but from an entirely different molecule, one yet to be identified or comprehended. This possibility opens avenues to chemistry that might be commonplace in the star system from which Atlas originated, yet entirely foreign to our cosmic vicinity. The brightening beyond projections. While the chromatic transformation dominates headlines, an equally significant development has been occurring in the comet's luminosity. As of mid-September, Atlas is exceeding all predictions, brightening at a rate far faster than any model deemed possible. The Comet Observation Database maintained by the CRNIV Observatory clearly depicts a deviation from expected behavior. Initially identified at magnitude 17, barely perceptible even to the most sensitive instruments, Atlas has surged to magnitudes 12 through 14 by the end of September. Its trajectory suggests it could reach magnitude 12 by late October, positioning it as the most luminous interstellar object ever observed, though still requiring telescopic aid for human sight. This rapid luminosity increase indicates a substantial escalation in outgassing activity. Dr. Adina Feinstein's team at Michigan State University, analyzing prediscovery images from NASA's Transiting Exoplanet Survey satellite, found evidence that this acceleration had been building since March, when Atlas was still beyond Jupiter's orbital path. The comet has been active at distances where comets within our solar system remain entirely quiescent. The implications extend beyond mere sublimation rates. University of Maryland's Kwani Y observes that Atlas's brightening pattern more closely resembles dynamically ancient comets from our own Oort cloud, objects that have completed numerous orbits within the inner solar system. Yet, this interpretation presents a paradox. How can an interstellar visitor, on its inaugural encounter with our Sun, exhibit characteristics of a comet with an extensive history of solar exposure? The sunward anomaly. Perhaps the most perplexing discovery emerged from a meticulous examination of Hubble Space Telescope images captured on July 21st. Avi Loeb and Eric Kito's investigation revealed something unprecedented in cometary science, an extended glow that stretches not away from the Sun, as conventional cometary tails do, but directly towards our star. This sunward extension, which they have termed an anti-tail, appears to be 10 times longer than the comet's width when adjusted for our viewing perspective. No comet in recorded history has exhibited such behavior. Traditional comet tails form as solar wind and radiation pressure propel material away from the nucleus. The physics governing an anti-tail pointing sunward challenges our fundamental understanding of how these objects interact with stellar environments. The implications reverberate across multiple scientific disciplines. If Atlas is generating some form of directed outgassing towards the Sun, the mechanism remains entirely enigmatic. Solar heating should result in symmetrical expansion or preferential outgassing from the Sun-facing hemisphere, not the focused, beam-like structure observed in Hubble's images. Some researchers have quietly begun exploring the possibility that Atlas might be exhibiting behavior inconsistent with a purely natural object. The alignment of its trajectory with the ecliptic plane, its unusual chemical composition, its anomalous brightening, its color transformation, and now the anti-tail, collectively form a pattern of characteristics that strains coincidence to uncomfortable limits. The chemical enigma deepens. Observations from the Very Large Telescope on August 25th unveiled another layer of mystery. Both cyanide and nickel production from Atlas increased dramatically as the comet approached the Sun, following a power law with an exponent of approximately 9. This represents one of the steepest production rate increases ever documented in cometary science. More intriguingly, the nickel appears without any accompanying iron, a combination that naturally occurs in only a limited number of specific contexts. Industrial nickel alloys manufactured through human metallurgy frequently exhibit this nickel without iron signature. While this does not inherently imply an artificial origin, it adds another unusual characteristic to an already anomalous object. The Webb Space Telescope's analysis revealed that the composition of Atlas's coma is predominantly carbon dioxide, comprising 87% by mass, with carbon monoxide making up 9%, and water accounting for most of the remaining 4%. This ratio significantly differs from both previously observed interstellar comets and typical solar system comets, suggesting formation conditions unlike anything found in our immediate cosmic vicinity. The rapid surge in cyanide production as Atlas nears the Sun raises questions about the stability of organic compounds within the nucleus. Cyanide, while naturally present in comets, typically appears at relatively consistent rates. The exponential increase observed in Atlas suggests either unconventional chemistry or structural properties that we have yet to comprehend. The Mars encounter. October 3rd marks a critical juncture in Atlas's trajectory through our solar system. The comet will achieve its closest proximity to Mars, passing within 28 million kilometers of the red planet. This presents an unparalleled opportunity for detailed observation utilizing spacecraft designed for Martian exploration. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter will direct their instruments towards the interstellar visitor, attempting spectroscopic analysis and imaging. Despite the comet appearing as less than a single pixel in their cameras, the high-resolution stereo camera and the color and stereo surface imaging system, typically focused on Martian topography, will instead peer into deep space, searching for insights into extraterrestrial chemistry. More importantly, these observations will occur during Atlas's most active phase, as solar heating drives peak outgassing rates. The spectrometers aboard both missions may detect additional chemical signatures that are beyond the resolution of Earth-based telescopes, potentially resolving the mystery of the green transformation or uncovering new complexities in the comet's composition. The timing also facilitates comparisons with NASA's Perseverance and Curiosity rovers, both equipped with instruments capable of atmospheric analysis. Although the rovers' primary missions concentrate on Martian geology and astrobiology, their atmospheric monitoring equipment might detect any particles or gases released by Atlas as it traverses the vicinity. The Jupiter connection. November brings another observational prospect as the European Space Agency's Jupiter Icy Moons Explorer, currently en route to the Jovian system, will attempt observations of Atlas utilizing multiple instruments. The spacecraft's position will offer a unique vantage point for studying the comet's behavior as it begins its outward trajectory from perihelion. The spacecraft carries ultraviolet spectrographs designed to analyze the chemical makeup of Jupiter's moons and magnetosphere. These instruments might detect spectral lines from Atlas that are undetectable from Earth due to atmospheric interference, potentially revealing the source of the mysterious green glow or identifying additional chemical signatures. Coordination with NASA's Europa Clipper mission offers the possibility of simultaneous observations from multiple perspectives, creating a three-dimensional view of Atlas's coma structure and activity patterns. The twin ultraviolet spectrographs on both spacecraft represent the most advanced instrumentation available for detailed chemical analysis of the comet during its most active period. However, technical challenges complicate these observations. The Jupiter Icy Moons Explorer is currently utilizing its main antenna as a heat shield during its close approach to the Sun, limiting communication to slower data rates via backup systems. Results from any Atlas observations may not reach Earth until February 2026. Months after the comet has passed perihelion and begun to dim. The second comet misconception. Amidst the burgeoning excitement surrounding Atlas, social media and certain news outlets have begun circulating claims about a second, even more massive comet entering our solar system. This narrative appears to stem from confusion between Atlas and comet Bernardinelli-Bernstein, officially designated C/2014 UN 271. Comet Bernardinelli-Bernstein is indeed colossal, with a nucleus diameter of approximately 140 kilometers, rendering it roughly 100 times larger than typical comets. However, this behemoth is not a recent arrival or a second interstellar visitor. Discovered in 2021 through the analysis of archived images dating back to 2014, Bernardinelli-Bernstein has been steadily approaching our inner solar system for years. The confusion intensifies because Bernardinelli-Bernstein is projected to reach its closest approach to the Sun in January 2031, still more than 5 years away. At its closest point, it will remain beyond Saturn's orbit, never venturing into the inner solar system where Earth and Mars orbit. While genuinely immense and scientifically compelling, it poses no threat and will not become visible to amateur astronomers. Recent observations have detected carbon monoxide jets erupting from Bernardinelli-Bernstein's nucleus, confirming its cometary nature and indicating increasing activity as solar heating penetrates its substantial mass. The Atacama Large Millimeter Array has mapped these jets, revealing asymmetric outgassing that suggests a complex nuclear structure and rotation. The fervor surrounding a second massive comet appears to be a consequence of misunderstanding the timeline and nature of Bernardinelli-Bernstein's approach. Social media algorithms, optimized for engagement rather than accuracy, have amplified these misconceptions, generating viral content that conflates multiple distinct astronomical objects and events. The trajectory mystery. Recent analysis by Zabia Perez-Cuto's team at the University of Arizona has traced Atlas's path backward through 10 million years of galactic motion, attempting to pinpoint its origin star system. The findings are both fascinating and frustrating. No single star system exhibits clear evidence of having ejected Atlas within the time frame suggested by its trajectory. This absence of an obvious parent system raises questions about the comet's true age and origin. If Atlas spent a significantly longer period than 10 million years traversing interstellar space, its point of origin becomes increasingly elusive. Gravitational interactions with multiple star systems could have altered its trajectory on numerous occasions, obscuring its original path. Alternatively, Atlas might originate from the galaxy's thick disk, a population of older stars distinct from the thin disk where our sun resides. Dr. James Davenport notes that the comet's galactic trajectory aligns with thick disk kinematics, suggesting formation around ancient, metal-poor stars that existed when our galaxy was young. This possibility renders Atlas not merely an interstellar visitor, but potentially a relic from the cosmic dawn, carrying chemical signatures from stellar environments that no longer exist. The unusual composition, including the dominance of carbon dioxide over water, might reflect formation conditions around stars with different metallicity than that found in our sun's neighborhood. The test discovery. Dr. Feinstein's analysis of transiting exoplanet survey satellite images revealed Atlas in photographs taken during May 2025, 2 months prior to its official discovery. These pre-discovery observations depict the comet already exhibiting significant activity at distances where solar system comets remain entirely dormant. The test images required sophisticated processing to extract the faint cometary signal from background stars and instrumental noise. By combining multiple exposures and filtering starlight, Feinstein's team revealed a fuzzy object showing clear signs of coma development. This confirms that Atlas commenced outgassing at approximately 6 astronomical units from the Sun, twice the distance of Jupiter's orbit. Such early activity suggests either an unusual volatile composition or structural characteristics that render Atlas more susceptible to solar heating than conventional comets. Data from the Zwicky Transient Facility extends observations back to March, when the comet was beyond Jupiter's orbit but already displaying detectable brightness variations consistent with active outgassing. This extended activity timeline provides crucial data for understanding Atlas's behavior as it approaches perihelion. The brightening rate adheres to a power law with an exponent of -3.8, significantly steeper than the interstellar comet Borisov, but consistent with dynamically ancient comets from our own solar system. The green chemistry puzzle. The September transformation to green emission presents one of the most intriguing enigmas in contemporary cometary science. Several mechanisms could potentially account for this sudden emergence of what appears to be diatomic carbon fluorescence, each carrying different implications for our understanding of Atlas's nature. Solar heating might have penetrated surface layers that previously shielded subsurface carbon compounds from sublimation. As Atlas approaches perihelion, escalating temperatures could reach deeper into the nucleus, accessing reservoirs of carbon-rich material that remained frozen throughout the comet's interstellar journey. Alternatively, the green glow might result from chemical reactions between previously segregated compounds, now brought together by the disruption of the nucleus's structure. Solar heating not only sublimes ices, it can fracture the porous structure of cometary nuclei, creating new pathways for volatile transport and mixing. A third possibility involves molecules other than diatomic carbon producing green fluorescence under specific excitation conditions. While diatomic carbon is the most common source of green cometary emission, other compounds can generate similar spectral signatures under particular circumstances. The unusual chemistry of Atlas might involve fluorescent molecules not typically encountered in solar system comets. The timing of the transformation, coinciding with increased solar heating as Atlas approaches perihelion, supports the thermal activation of previously dormant chemical processes. However, the abruptness of the change suggests a threshold effect rather than gradual activation, implying complex chemistry or structural alterations within the nucleus. The polarization anomaly. Recent polarimetric observations have revealed another unusual characteristic of Atlas. The comet exhibits an exceptionally deep negative polarization of -2.77%, with a low inversion angle of 6.41 degrees. These values position Atlas outside the typical range for both solar system comets and previously observed interstellar comets. Analysis of light polarization provides insight into the size, form, and makeup of dust motes within the comet's coma. The peculiar polarization pattern suggests that Atlas expels dust with properties markedly different from typical cometary constituents. This divergence could signify an unusual composition, distinct formation circumstances, or structural alterations acquired during its interstellar sojourn. The observed negative polarization at shallow phase angles, coupled with a low inversion angle, points to dust grains possessing high albedo and atypical optical characteristics. Such traits might stem from coatings of organic compounds, crystalline structures formed during slow cooling in interstellar space, or a composition dominated by substances seldom found in our solar system. These polarimetric readings offer independent validation that Atlas differs fundamentally from both solar system comets and other documented interstellar visitors. The confluence of peculiar chemistry, anomalous brightness, mysterious green metamorphosis, and characteristic polarization creates a profile unmatched by any object studied thus far. The question of nuclear composition. Hubble Space Telescope observations have progressively refined estimations of Atlas's nuclear dimensions, with recent analyses indicating a diameter ranging from 440 meters to 5.6 kilometers. This span, covering nearly an order of magnitude, reflects the difficulty in distinguishing the nucleus's brightness from the surrounding coma emission. The ambiguity in nuclear size directly influences calculations of mass, density, and composition. A smaller nucleus would necessitate higher activity rates to account for the observed coma brightness, suggesting either structural attributes that boost outgassing efficiency. Conversely, a larger nucleus could contain greater reserves of exotic ices while maintaining normal activity levels. Spectroscopic analysis indicates that the nucleus itself may be exceptionally dark, reflecting only a minor fraction of incoming sunlight. This low albedo could result from organic compounds formed during irradiation in interstellar space, a carbon-rich composition reflecting formation conditions around different star types, or surface modifications during the comet's extensive voyage between star systems. The combination of uncertain size and low reflectivity complicates efforts to comprehend Atlas's internal structure and composition. Sophisticated thermal modeling, incorporating data from multiple wavelengths and observational viewpoints, may eventually resolve these uncertainties as the comet nears its peak activity around perihelion. The activity profile Atlas exhibits an activity profile unlike any comet observed previously, initiating significant outgassing at distances where solar system comets remain entirely inactive. This early activation suggests a composition dominated by highly volatile substances that sublimate at lower temperatures than water ice. The steep brightening curve, characterized by a power law exponent of -3.8, indicates rapidly escalating activity as the comet approaches the Sun. This behavior mirrors that of dynamically old comets originating from our own Oort cloud, objects that have undergone multiple passages through the inner solar system and developed enhanced volatile transport mechanisms. However, Atlas is purportedly making its initial approach to any star system since its ejection from its parent system millions or billions of years ago. The contradiction between its pristine interstellar status and its aged comet-like behavior suggests either unconventional formation conditions or modifications during its interstellar transit that have conferred characteristics typically associated with solar exposure. Recent observations reveal that both dust and gas production rates escalate exponentially with decreasing solar distance, following power laws with exponents approaching 9 for specific chemical species. This extreme sensitivity to solar heating implies either very shallow subsurface volatile reserves or enhanced heat transfer mechanisms within the nucleus. Spacecraft observations. Numerous spacecraft operating throughout the solar system will attempt to observe Atlas during its closest approach to the Sun, providing unparalleled multi-angle coverage of an interstellar visitor. These observations encompass various electromagnetic wavelengths and observational geometries, yielding the most comprehensive dataset ever compiled for an object of this nature. NASA's Parker Solar Probe, engineered to investigate the Sun's corona, will observe Atlas using its Wide-Field Imager for the Solar Probe instrument during late September through early November. This time frame encompasses the comet's perihelion passage and offers perspectives from closer to the Sun than any other observatory can achieve. The Lucy mission, en route to study Jupiter's Trojan asteroids, may capture images of Atlas from its unique vantage point in the outer solar system. Similarly, NASA's Psyche mission, traveling towards the metal-rich asteroid 16 Psyche, passed in close proximity to Atlas on September 4th, although no images have been publicly released to date. The most compelling observations may originate from ESA's Hera mission, launched to study the aftermath of NASA's DART impact on asteroid Dimorphos. Hera's instruments, designed for detailed surface mapping and compositional analysis, could offer unprecedented views of Atlas's nuclear structure during its approach phase. The communication challenge. Several planned observations encounter significant technical hurdles related to spacecraft positioning and communication constraints. Jupiter Icy Moons Explorer, potentially offering the most advantageous views of Atlas during its peak activity, is currently unable to transmit data at normal rates due to its proximity to the Sun, necessitating antenna shielding. The spacecraft's primary high-gain antenna functions as a heat shield during close solar approaches, compelling communication through smaller backup antennas with severely restricted bandwidth. This limitation means that any data transmitted during Atlas's perihelion passage and subsequent fading will be significantly delayed. Europa Clipper faces comparable challenges as it traverses the inner solar system en route to its eventual Jupiter destination. The spacecraft's instruments are optimized for icy moon analysis rather than cometary observation, although its ultraviolet spectrographs may detect spectral signatures imperceptible to Earth-based telescopes. Coordinating observations from multiple spacecraft demands precise timing and data correlation to maximize scientific returns. The difficulties of interplanetary communication, coupled with the brief observational windows as Atlas races through the inner solar system, necessitate careful planning and realistic expectations for data acquisition. The theoretical implications. The accumulating anomalies associated with Atlas challenge several foundational assumptions regarding interstellar objects and cometary science. The convergence of an unusual trajectory alignment, distinctive chemical composition, anomalous brightness behavior, mysterious color transformation, and unprecedented sunward glow creates a pattern that defies straightforward explanation. Some researchers are beginning to investigate whether Atlas represents a novel category of interstellar object, perhaps formed under conditions absent in our solar system's region of the galaxy. The early activation of outgassing and the unusual nuclear composition might reflect formation around diverse stellar types possessing distinct chemical signatures. The possibility that Atlas originates from the galaxy's thick disk raises questions about stellar nucleosynthesis in early galactic history. If this interpretation proves accurate, the comet carries chemical imprints from stellar environments that existed when our galaxy was young, offering direct samples of ancient stellar processing. Alternative explanations range from conventional, yet unusual natural processes to scenarios that push the boundaries of current scientific understanding. The alignment with the ecliptic plane, in conjunction with other anomalies, has prompted some researchers to explore whether Atlas might be something other than a typical comet. The October climax. As October progresses towards the 13th, Atlas will achieve its closest approach to the Sun, marking the zenith of its journey through our solar system. This perihelion passage, occurring at approximately 1.4 astronomical units, positions the comet between the orbits of Earth and Mars at its moment of maximum solar heating. The period surrounding perihelion represents the prime opportunity for scientific observation, as outgassing rates reach their highest levels and the comet's true nature becomes most apparent. However, the comet's position relative to Earth during this crucial phase places it on the opposite side of the Sun, rendering ground-based observations exceedingly challenging. Solar conjunction. When Atlas appears near the Sun in Earth's sky, will render the comet unobservable from our planet during its most active period. This frustrating timing implies that the most dramatic developments in Atlas's evolution may occur beyond the reach of our most powerful terrestrial telescopes. Space-based observatories, including those aboard Mars orbiters and the various spacecraft dispersed throughout the solar system, become indispensable for maintaining observational coverage during this critical interval. The Parker Solar Probe, specifically engineered to operate in the harsh environment near the Sun, may provide the sole detailed observations of Atlas at perihelion. The outbound journey. Following its perihelion passage, Atlas will commence its lengthy voyage back into interstellar space, never to revisit our solar system. The outbound observations, commencing in early November as the comet emerges from solar conjunction, will reveal how the intense solar heating has altered its nucleus and activity patterns. Many comets undergo dramatic transformations during perihelion passage, with some fragmenting under thermal stress, while others develop novel outgassing patterns that persist for months or years. Atlas's behavior during its outbound journey will furnish crucial insights into its internal structure and composition. The fading phase of Atlas's visit presents opportunities to study how an interstellar object responds to intense solar heating and whether the experience engenders lasting modifications. Changes in brightness, spectral characteristics, or coma structure during the outbound journey could illuminate how thermal cycling impacts materials formed in other star systems. By early 2026, Atlas will have dimmed beyond the observational range of most telescopes. Returning to the interstellar medium, carrying whatever modifications its solar encounter has induced, the comet will spend the ensuing several million years traversing the void between stars, potentially transporting Earth-based contaminants or solar system signatures to distant reaches of our galaxy. The long-term questions. Atlas's brief sojourn raises profound inquiries about the frequency and nature of interstellar visitors to our solar system. If such objects pass through regularly, as some models propose, our solar system exists within a continuous flow of material from other star systems, creating ongoing possibilities for chemical and potentially biological exchange. Atlas's unusual characteristics suggest that interstellar objects may be far more diverse than the limited sample we have observed indicates. Each visitor carries unique imprints of its formation environment, potentially shedding light on stellar conditions across our galaxy's history and various spatial regions. Future surveys, including the Veris C. Rubin Observatory, slated for commencement soon, will dramatically increase our detection rate for interstellar objects. The observatory's broad field coverage and sensitive instrumentation may uncover dozens of visitors akin to Atlas, thereby establishing a substantial dataset for comparative analysis. The European Space Agency's Comet Interceptor mission, conceived specifically to study pristine comets and potentially interstellar visitors, represents the next generation of exploration tools for these celestial bodies. Unlike sample return missions that necessitate years of advanced planning, Comet Interceptor will remain on standby, prepared to investigate any suitable target that emerges with adequate advance notice. The detection revolution. The discovery of Atlas exemplifies how modern survey capabilities have revolutionized our capacity to detect and study interstellar objects. The network of Atlas telescopes, complemented by archives from the Zwicky Transient Facility and other surveys, provides comprehensive coverage ensuring that few bright interstellar visitors will evade detection. Artificial intelligence and machine learning algorithms now automatically scan millions of astronomical images, identifying moving objects and anomalous signatures that might suggest an interstellar origin. These systems can process observational data faster than human astronomers, enabling prompt follow-up observations while the objects remain accessible. The integration of space-based and ground-based observatories establishes multiple independent detection pathways, with instruments such as the Transiting Exoplanet Survey satellite offering additional coverage that fills gaps in ground-based monitoring. This redundancy ensures that interstellar objects like Atlas can be detected and studied even when initially too faint for any single survey. Advanced data sharing protocols facilitate rapid dissemination of discovery information to observatories worldwide, enabling coordinated follow-up observations that maximize scientific returns. The Minor Planet Center's automated notification systems ensure that significant discoveries reach the global astronomical community within hours of initial detection. The chemical database. Each interstellar visitor contributes unique data to our expanding repository of chemical compositions from other star systems. Atlas's unusual carbon dioxide dominance, coupled with distinctive nickel signatures and the absence of expected iron, provides information regarding stellar nucleosynthesis and planetary formation processes in different galactic environments. Comparisons between Atlas, previous visitors, Oumuamua and Borisov, and future interstellar objects will reveal whether common formation processes prevail throughout our galaxy or if each star system yields distinct chemical signatures. The diversity observed thus far suggests significant variation in stellar environments and planetary system evolution. Spectroscopic databases compiled from multiple interstellar visitors may eventually enable the determination of object origins through chemical fingerprinting. Different stellar populations across our galaxy should produce characteristic elemental ratios and molecular compositions that serve as markers of their formation environments. The accumulating data also provides crucial input for theoretical models of galactic chemical evolution, stellar nucleosynthesis, and planetary system formation. Direct samples from other star systems offer unprecedented opportunities to test models that previously relied solely on astronomical observations and laboratory experiments. The contamination question. As Atlas traverses our solar system, it potentially acquires contaminants from solar wind particles, interplanetary dust, and even traces of Earth's atmosphere that escape into space. This acquired material will accompany the comet back into interstellar space, carrying chemical signatures of our solar system to distant galactic regions. The prospect of biological contamination, while exceedingly remote, raises intriguing questions about the interstellar transfer of organic material. Earth's upper atmosphere harbors microorganisms that might theoretically survive transfer to passing interstellar objects, although the extreme conditions of space make such survival highly improbable. More significantly, Atlas may carry industrial signatures from human activity, including isotopic ratios characteristic of nuclear technology and synthetic compounds produced exclusively by technological civilizations. Should the comet eventually encounter other star systems, these signatures could serve as evidence of technological activity within our solar system. The inverse possibility that Atlas carries signatures from its origin system drives much current research into the comet's composition and characteristics. Any unusual elements, isotopic ratios, or organic compounds could provide direct evidence of conditions around other stars or even biological processes in distant planetary systems. Future visitors. Statistical models indicate that objects such as Atlas pass through our solar system with regularity, perhaps several times per decade, though most remain too faint for detection with current technology. The Vera-C, Rubin Observatory, and other next-generation surveys will dramatically enhance our detection sensitivity, revealing a continuous influx of interstellar visitors. Each new detection will augment our understanding of galactic populations, stellar system characteristics, and the prevalence of planetary formation throughout our cosmic neighborhood. The accumulating data may unveil patterns in visitor characteristics that reflect the structure and evolution of our galaxy's stellar populations. Advanced mission concepts currently under development include rapid-response spacecraft capable of intercepting interstellar objects with minimal advance warning. These missions will be equipped with sophisticated analytical instruments for detailed in-situ studies unattainable through ground-based observations. The European Space Agency's Comet Interceptor represents the inaugural mission of this kind, designed to rendezvous with a pristine comet or interstellar object for in-depth investigation. Future missions may incorporate sample return capabilities, bringing material from other star systems directly to Earth-based laboratories for comprehensive analysis. The technology evolution. The study of Atlas demonstrates how rapidly advancing technology enhances our capacity to investigate cosmic visitors. Advanced spectroscopic techniques, machine learning algorithms for data analysis, and coordinated multi-wavelength observations create research capabilities surpassing those available for previous interstellar objects. Future technological advancements will further expand our investigative toolkit. Next-generation space telescopes, including successors to the James Webb Space Telescope, will provide unparalleled spectroscopic resolution for studying faint interstellar objects. Advanced coronagraph systems may enable detailed observations even when objects appear close to the Sun. Artificial intelligence systems trained on extensive databases of astronomical observations will identify subtle patterns and anomalies that human researchers might overlook. These systems may detect evidence of unusual composition, artificial origin, or exotic physics in ways that complement traditional analytical approaches. The integration of quantum sensing technologies, advanced materials science, and sophisticated computational modeling creates novel possibilities for understanding objects that spend only brief periods within observational range. These tools may unveil secrets of interstellar visitors that remain concealed with current technology. The philosophical implications. Atlas's passage through our solar system prompts profound questions about our position within the galaxy and the nature of the cosmic environment surrounding Earth. We exist within a dynamic system where material perpetually flows between star systems, forging connections across vast distances and temporal scales. The possibility that some interstellar visitors might be artificially created objects, while scientifically contentious, compels consideration of how we might recognize evidence of other civilizations. Atlas, though likely natural in origin, exemplifies the challenges in distinguishing artificial from natural phenomena. The astonishing chemical variety observed in cosmic wanderers hints that our own solar system might be merely one instance among countless variations found throughout the Milky Way galaxy. The specific circumstances that fostered life on our planet could be commonplace, exceedingly rare, or utterly singular, contingent upon the prevalence of the fundamental chemical building blocks for biology in other stellar nurseries. The brief temporal windows afforded for studying celestial visitors from beyond our solar system underscore both our present observational constraints and the immense scale of cosmic phenomena that elude our detailed comprehension. Each celestial sojourner carries within it a narrative of distant cosmic expanses and epochs. Yet, our fleeting chances for scrutiny capture only slivers of these grand cosmic chronicles, a limitation mirrored by our observational networks. The extensive international cooperation necessitated for even a rudimentary study of these visitors underscores how contemporary astrophysics has transcended terrestrial frontiers and institutional confines. Observatories situated across 6 continents are meticulously synchronizing their observations, exchanging data through advanced interconnected systems that facilitate real-time analysis of phenomena undergoing rapid transformation. The Atlas survey system stands as a prime illustration of this unified global strategy, with telescopes strategically positioned in Chile, South Africa, and Hawaii, providing uninterrupted surveillance of the entirety of the observable heavens. The instant the Chilean observatory's instruments first registered the presence of Atlas on the first day of July, the momentous discovery instantly triggered automated alerts that disseminated to observatories across the globe within mere minutes. Terrestrial observation networks are now seamlessly integrated with extraterrestrial assets, creating comprehensive observational campaigns that span the electromagnetic spectrum, from radio telescopes anchored to Earth's surface to ultraviolet spectrographs orbiting far above our atmosphere. The James Webb Space Telescope's observations of Atlas are being meticulously coordinated with simultaneous measurements from the Hubble Space Telescope, thereby generating multi-wavelength datasets that would be utterly unattainable with any single observatory. Citizen scientists are making invaluable contributions to these collaborative endeavors, with grassroots networks such as the Unistellar system offering distributed observations that skillfully complement the work of professional facilities. The remarkable detection of the object's green transformation by Michael Jerger and Gerald Raymond exemplifies how dedicated amateur observers frequently capture pivotal developments that larger professional surveys might inadvertently overlook. The established protocols for data sharing, meticulously developed for ATLAS observations, will serve as foundational templates for the investigation of future interstellar voyagers. Standardized data formats, robust rapid communication channels, and synchronized observing schedules are designed to maximize the scientific yield derived from objects that grace our skies for only ephemeral durations. This presents a considerable computational undertaking. The sheer volume of data generated by ATLAS observations necessitates computational power and algorithmic sophistication that are continually pushing the boundaries of current technological capabilities. Every night of observation from major telescopes produces terabytes of raw data, requiring extensive processing, calibration, and analysis before any meaningful scientific interpretation can even commence. Sophisticated machine learning algorithms, trained on vast archives of cometary observations, are employed to discern patterns and anomalies within ATLAS's behavior that human researchers might not readily detect. These automated systems meticulously analyze variations in brightness, shifts in spectral characteristics, and evolutionary changes in morphology across thousands of images with a consistency and speed that manual examination could never hope to achieve. Advanced atmospheric models, incorporating data from multiple spacecraft, are being utilized to elucidate how ATLAS's outgassing interacts with the solar wind and the interplanetary magnetic field. The computational demands for these simulations are immense, requiring supercomputing resources to accurately model the intricate physics governing gas and dust dynamics within the unforgiving environment of interplanetary space. Precise calculations of orbital mechanics are employed to trace ATLAS's trajectory backward through millions of years of galactic movement, meticulously accounting for gravitational influences from countless stellar encounters during its interstellar passage. These complex computations shed light on probable origin regions while simultaneously highlighting the inherent uncertainties that permeate the reconstruction of ancient cosmic pathways. The synergistic integration of observational findings with theoretical models fosters feedback loops that progressively refine our understanding of cometary physics, galactic dynamics, and the multifaceted properties of interstellar space. Each new piece of empirical data serves to constrain theoretical possibilities while simultaneously revealing emergent complexities that necessitate further inquiry. The unresolved isotopic enigmas. High-resolution spectroscopy applied to ATLAS has the potential to reveal isotopic ratios that can furnish direct insights into the nuclear processes occurring within its parent star system. Stars of differing masses and evolutionary stages imprint characteristic isotopic signatures, which serve as unique identifiers of their internal thermonuclear furnaces. The observed ratio of carbon to nitrogen within ATLAS's coma already suggests formation conditions that diverge significantly from the environment of our solar system. As the precision of spectroscopic measurements continues to advance, additional elemental ratios may illuminate whether this celestial body coalesced around a star possessing a mass, age, or metallicity distinct from that of our Sun. Isotopic analysis demands extraordinarily high spectral resolution and signal-to-noise ratios, challenges that are currently testing the limits of our observational capabilities. The inherent faintness of ATLAS, coupled with its rapid traversal of the celestial sphere, imposes strict limitations on exposure times and complicates the precise measurements crucial for isotopic determination. Future space-based spectrographs, endowed with enhanced sensitivity and stability, may eventually enable detailed isotopic analysis of interstellar visitors, thereby yielding direct measurements of stellar nucleosynthesis processes throughout our galaxy. Such empirical data would provide an unprecedentedly precise means of testing theories concerning galactic chemical evolution. The potential discovery of isotopic ratios that are demonstrably impossible to generate within any known stellar environment would herald a revolution in our comprehension of nuclear physics, or point towards exotic formation scenarios that lie beyond our current theoretical frameworks. Such groundbreaking findings would undoubtedly be counted among the most significant scientific achievements in modern astronomical history. The thermal transformation as ATLAS approaches perihelion. Thermal modeling endeavors to predict how the Sun's increasing heat will influence the nucleus's internal structure and chemical makeup. The unusual activity patterns observed thus far suggest intrinsic characteristics that substantially differ from those typically exhibited by comets within our solar system. The degree to which heat penetrates the nucleus is influenced by factors including porosity, composition, thermal conductivity, and rotation rate, most of which remain poorly quantified for ATLAS. The premature onset of activity implies either a remarkably low thermal inertia or a composition dominated by highly volatile substances. Subsurface temperature gradients dictate the timing and intensity of outgassing as various chemical species reach their sublimation points at different depths within the nucleus. The abrupt escalation in activity observed with ATLAS suggests either rapid thermal ingress or unusually shallow reservoirs of volatile compounds. Sophisticated computer simulations are employed to model diverse nucleus compositions and structures, aiming to replicate the observed brightness and spectral variations. These simulations posit that ATLAS may possess a layered internal structure, with distinct distributions of volatile materials at varying depths, potentially reflecting its unique formation history or modifications incurred during its interstellar voyage. The striking color alteration from red to green signifies chemical transformations or structural changes that expose fresh material to solar radiation. A comprehensive understanding of these dynamic processes necessitates intimate knowledge of how heat propagates through porous, heterogeneous materials under the extreme conditions of space. The magnetic milieu. ATLAS navigates through the intricate magnetic environment of interplanetary space, where the solar wind carries embedded magnetic fields that interact with the electrically charged particles within the comet's coma. These interactions give rise to observable phenomena that may be discernible with appropriately equipped instrumentation. Charged dust grains and ions within the coma are susceptible to magnetic forces, potentially leading to the formation of asymmetric structures or preferred directions of outflow, contingent upon the orientation of the local magnetic field. Such influences could provide explanations for some of the peculiar morphological features observed in ATLAS's coma. The Parker Solar Probe, specifically engineered to investigate the properties of the solar wind and the structure of its magnetic field, may potentially detect signatures of ATLAS's interaction with its interplanetary surroundings during their close proximity near perihelion. These measurements could elucidate how interstellar objects exert an influence on local space conditions. Magnetic field measurements obtained from spacecraft operating throughout the solar system provide crucial context for understanding the extent to which ATLAS's passage perturbs the broader interplanetary environment. The outgassing from the comet generates a subtle yet measurable disturbance in the solar wind, which propagates across millions of kilometers. Advanced plasma physics simulations are employed to model the complex interplay between the solar wind, the interplanetary magnetic field, and ATLAS's coma, aiming to predict observable signatures and elucidate the underlying physical processes. These simulations necessitate sophisticated numerical techniques and substantial computational resources. The dynamics of dust. The peculiar polarization characteristics of ATLAS indicate that its constituent dust particles diverge significantly from those typically found in comets within our solar system. These distinctions may be indicative of variations in formation conditions, modifications sustained during interstellar travel, or compositional differences that impact particle structure and optical properties. Analysis of dust grains, utilizing measurements of scattered light, seeks to ascertain particle size distributions, chemical compositions, and morphologies that govern ATLAS's interaction with solar radiation. The pronounced negative polarization observed suggests the presence of particles possessing distinctive optical properties. Radiation pressure exerted by the sun accelerates dust particles away from ATLAS's nucleus, engendering the visible coma and potentially contributing to tail formation. The efficiency of this process is contingent upon particle size, composition, and optical properties that remain poorly understood for interstellar material. Advanced scattering models integrate a range of particle compositions and structures to align with observed polarization and brightness measurements. These models infer that ATLAS may eject particles with intricate morphologies or exotic compositions not typically encountered in cometary dust. The interaction between charged dust particles and the interplanetary magnetic field introduces further complexity into dust dynamics, potentially resulting in asymmetric dust distributions or preferred ejection trajectories that contribute to the unusual morphological features observed in Hubble images. The evolving spectral signature. ATLAS's spectral signature continues to transform as changing solar heating triggers distinct chemical processes within its nucleus. This evolution offers a real-time glimpse into the responsiveness of interstellar material to stellar radiation. Initial observations, predominantly characterized by carbon dioxide emissions, are gradually yielding to more complex spectra as additional molecular species attain their sublimation temperatures. The striking increase in cyanide production exemplifies how evolving conditions activate novel chemical pathways. High-resolution spectroscopy reveals Doppler shifts within emission lines, indicative of expansion velocities and outflow patterns within the coma. These measurements serve to constrain models of gas dynamics and aid in differentiating between various outgassing mechanisms. The abrupt emergence of green emissions suggests the activation of chemical reactions involving carbon-bearing molecules, although the precise compounds responsible remain uncertain. Continued spectroscopic monitoring may facilitate the identification of the molecules responsible for this dramatic color transition. Subsequent observations will meticulously track how Atlas's spectrum evolves through its perihelion passage and into its outbound trajectory, thereby illuminating how thermal cycling influences chemical processes in material that originated around distant stars. This temporal evolution provides unparalleled insights into the intricacies of interstellar chemistry. The risk of fragmentation. The intense solar heating experienced during perihelion passage poses a significant threat of nuclear fragmentation for Atlas, potentially jeopardizing our opportunity to study an intact interstellar object. Numerous comets succumb to structural failure when thermal stresses surpass their mechanical resilience. The unusual activity patterns and rapid brightening observed in Atlas may signal internal structural modifications that compromise its resistance to thermal strain. Early outgassing could have instigated internal fractures or weakened regions that subsequently act as failure points under intense heating. Monitoring for indicators of fragmentation necessitates high-resolution imaging capable of discerning small fragments detaching from the main nucleus. Such observations demand exceptional atmospheric seeing conditions and sophisticated image processing techniques to differentiate genuine fragments from transient brightness fluctuations. The Hubble Space Telescope, with its remarkable angular resolution, stands as the preeminent instrument for detecting potential fragmentation events. However, the comet's proximity to the Sun during perihelion significantly curtails observational opportunities precisely when the risk of fragmentation is at its zenith. Fragmentation would profoundly alter Atlas's subsequent trajectory, potentially generating a stream of debris that offers multiple targets for spectroscopic analysis, while simultaneously diminishing the intensity of individual fragments below detectable thresholds. The mechanisms of outgassing, the precise physical processes driving Atlas's atypical outgassing patterns, remain poorly understood despite extensive observational and theoretical efforts. The early activation, rapid brightening, and unusual chemical composition point towards mechanisms distinct from the conventional sublimation observed in comets. Direct sublimation from the nuclear surface cannot account for the observed levels of activity at considerable solar distances, suggesting either enhanced internal heat transfer within the nucleus or chemical processes involving more volatile constituents than water ice. Carbon dioxide sublimation occurs at lower temperatures, but requires unusually high concentrations to adequately explain the observed activity. Subsurface sublimation followed by the migration of gas through porous networks within the nucleus could account for some of the anomalous features observed. However, this mechanism necessitates specific structural characteristics that may not be applicable to interstellar objects possessing divergent formation histories. Explosive outgassing, triggered by phase transitions, crystallization events, or chemical reactions, could produce the rapid brightness fluctuations observed in Atlas. Such processes might be initiated by solar heating, but operate through mechanisms fundamentally different from simple sublimation. The anomalous sunward extension of scattered light suggests directed outgassing or unusual particle dynamics that current models struggle to adequately explain. Comprehending this phenomenon requires the development of novel theoretical frameworks that may be applicable to interstellar objects, but not necessarily to their solar system counterparts. The chemical inventory. The steadily expanding catalog of chemical species detected within Atlas offers an increasingly detailed portrayal of its composition and the conditions that prevailed in its original formation environment. Each newly identified molecular species provides additional constraints for models of stellar nucleosynthesis. Water, carbon dioxide, carbon monoxide, cyanide, and a variety of organic compounds constitute a chemical inventory that notably deviates from that of typical comets. The pronounced dominance of carbon dioxide over water, in particular, stands out as an unusual characteristic for objects originating in our cosmic vicinity. The detection of trace species necessitates exceptionally sensitive spectroscopic techniques that push the boundaries of observational capabilities. Each additional molecular identification furnishes critical information regarding formation conditions and evolutionary history. The conspicuous absence of certain anticipated species can be as illuminating as positive detections, suggesting formation environments that lack the typical chemistry of comets or evolutionary processes that have modified the original composition through chemical reactions or selective depletion. Comparisons with laboratory experiments simulating ice chemistry under various temperature and radiation conditions aid in interpreting the observed molecular inventory and constraining the physical conditions that Atlas likely experienced during its formation and interstellar journey. The structure of the nucleus. Elucidating the internal structure of Atlas's nucleus presents fundamental challenges owing to its diminutive size and considerable distance from Earth. Current observations provide only indirect inferences regarding its density, porosity, composition, and structural integrity. The correlation between the nucleus's size and its observed activity suggests either an exceptionally high volatile content or an enhanced efficiency of heat transfer when compared to typical comets. These characteristics may be a consequence of its formation conditions or structural modifications sustained during interstellar travel. Thermal modeling attempts to deduce the internal structure from observed outgassing patterns. While multiple structural scenarios can produce similar observational signatures, distinguishing between divergent models necessitates additional data from future observations. Determining the rotation period could yield insights into the nucleus's shape and density distribution, though detecting brightness variations from such a distant object poses a significant challenge for current observational capabilities. Long-term photometric monitoring may eventually reveal rotational signatures. The peculiar polarization properties suggest surface or near-surface characteristics that differ from those of typical cometary nuclei, possibly indicating compositional variations, structural modifications, or the presence of exotic materials not found in solar system objects. The environment of formation. The chemical composition and physical attributes of Atlas offer valuable clues about the stellar environment in which it coalesced billions of years ago. These ancient signatures preserve information regarding stellar nucleosynthesis and planetary system evolution within diverse galactic contexts. The unusually high concentration of carbon dioxide suggests formation within a stellar system exhibiting different carbon-to-oxygen ratios than our own solar system, possibly around stars with varying masses, ages, or metallicities. Such variations profoundly influence the chemical building blocks available for planetary formation. Isotopic ratios, once they are eventually determined, will provide direct evidence of the nuclear processes within the parent star and serve to refine models of stellar evolution and galactic chemical evolution. These measurements represent our most direct avenue for studying stellar nucleosynthesis beyond the confines of our solar system. The inferred age of Atlas, potentially spanning billions of years, indicates its formation during a period when our galaxy possessed a different chemical composition and a distinct population of stars compared to the present day. The study of this ancient visitor offers insights into the grand sweep of cosmic chemical evolution over galactic timescales. Comparing Atlas with other interstellar objects and comets within our solar system will reveal whether its anomalous characteristics are representative of typical conditions found in other stellar systems, or if they signify an exotic formation environment that is now either exceedingly rare or entirely absent in our galactic neighborhood. The trajectory analysis, involving detailed orbital calculations for Atlas, aims to retrace its path backward through millions of years of galactic motion to pinpoint its putative origin star system. These computations require sophisticated models of galactic dynamics and stellar kinematics. The comet's present trajectory aligns closely with the galactic plane, suggesting formation within the thick disk of stars rather than the thin disk region where our sun resides. This alignment provides crucial indicators regarding its probable origin environment. Gravitational perturbations from stellar encounters experienced during Atlas's interstellar journey have likely altered its original trajectory, making precise origin determination increasingly challenging for more ancient objects. Statistical analysis can still identify probable source regions even when specific parent stars remain elusive. The high velocity of Atlas relative to our solar system suggests either its ejection from a high-velocity stellar system or acceleration through gravitational interactions during its interstellar passage. Understanding these complex dynamics necessitates meticulous modeling of galactic structure and stellar motions. Subsequent astrometric determinations will refine Atlas's orbital trajectory and enhance its path reconstructions, potentially pinpointing further evidence regarding its origins, geographical locale, and developmental trajectory. The enduring observational impact of the comprehensive observational effort dedicated to Atlas sets novel benchmarks for the examination of transient celestial events and showcases the efficacy of contemporary, harmonized astronomical practices. The methodologies devised for this inquiry will prove beneficial for subsequent investigations of comparable celestial bodies. Archival data sourced from numerous surveys, extending back several months prior to its official identification, underscore the significance of maintaining thorough sky surveillance systems. These archives facilitate the reconstruction of an object's developmental progression through periods where no targeted observations were conducted. The amalgamation of professional and amateur astronomical contributions fosters observational networks exhibiting spatial and temporal coverage unattainable by any single organization. Contributions from citizen scientists prove especially valuable for observing phenomena that evolve rapidly. Standardized data formats and swift communication protocols established for Atlas observations will streamline future coordinated campaigns, enabling a more effective utilization of limited observation windows for ephemeral celestial objects. The insights gained from studying Atlas inform the blueprint for forthcoming survey systems and spacecraft missions, emphasizing the observational capacities requisite for maximizing scientific yield from fleeting encounters with interstellar interlopers. Theoretical frameworks. The peculiar attributes of Atlas challenge established theoretical paradigms for comprehending cometary physics, necessitating the development of novel models capable of accommodating interstellar objects exhibiting properties beyond the spectrum observed within our solar system. Traditional sublimation models predicated on water-ice physics falter in explaining the premature activity and swift luminescence observed in Atlas, thus requiring the integration of more volatile constituents and intricate thermal processes to align with empirical findings. The sunward extension of scattered light runs counter to established understanding of radiation pressure and dust dynamics surrounding comets, suggesting either the presence of exotic particle characteristics or novel physical mechanisms previously unobserved or theoretically posited. Advanced computational simulations, incorporating intricate chemistry, multi-component physics, and three-dimensional architectures, strive to replicate the full spectrum of observed phenomena. These simulations necessitate substantial computational resources and sophisticated numerical methodologies. The advancement of theoretical frameworks capable of elucidating Atlas's behavior propels our collective understanding of cometary physics forward and readies us for the exploration of future interstellar visitors that may exhibit equally extraordinary attributes. Detection statistics. The frequency of discovering interstellar objects has surged dramatically with enhanced survey capabilities, indicating that such visitors may be far more prevalent than previously believed. Statistical analyses aim to ascertain the true population size and incidence of these cosmic wanderers. 3 confirmed interstellar objects detected within an 8-year span suggest a substantially larger population of fainter objects that elude detection with current technological means. The advent of advanced surveys will dramatically augment our detection sensitivity and reveal the true prevalence of interstellar visitors. Population models extrapolate from current detections to estimate the total number of interstellar objects traversing our solar system annually. These models indicate that several objects exceeding 100 meters in diameter may pass through our cosmic vicinity each year. The size distribution of detected interstellar objects displays a pronounced observational bias toward larger, more active specimens. Future surveys with heightened sensitivity will clarify whether smaller interstellar objects adhere to the same size distributions observed for solar system comets and asteroids. Long-term monitoring of interstellar object detection rates will provide constraints for models of galactic stellar populations and planetary system evolution, yielding insights into the efficacy of planetary formation processes across our galactic neighborhood. Mission planning. The limited advance notice provided by current detection systems severely curtails our capacity to launch dedicated missions for the detailed study of interstellar objects. Future mission concepts must accommodate rapid response imperatives or remain on standby for suitable targets. The European Space Agency's Comet Interceptor mission represents the inaugural spacecraft specifically engineered for the investigation of pristine comets and potentially interstellar objects. This mission architecture permits the examination of targets identified with minimal prior warning. Advanced propulsion concepts currently under development could facilitate more ambitious interstellar object missions, including sample return capabilities that would transport material from other star systems directly to terrestrial laboratories for comprehensive analysis. Rapid response mission concepts demand pre-positioned spacecraft, advanced propulsion systems, and streamlined mission planning procedures that can be activated swiftly when suitable targets emerge. These capabilities necessitate novel approaches to space mission conception and execution. The scientific dividends derived from dedicated interstellar object missions would substantially surpass those achievable from remote observations alone, furnishing detailed compositional analyses, internal structural determinations, and direct sampling of extraterrestrial materials. Public interest. The identification and unusual comportment of Atlas have captivated the public imagination to a degree rarely achieved by conventional astronomical discoveries. The confluence of mystery, potential ramifications, and striking visual observations engenders compelling narratives that resonate with a wide spectrum of audiences. Social media engagement concerning Atlas exemplifies both the advantages and difficulties of swift information dissemination in the digital era. Accurate scientific information contends with sensationalized assertions and speculative interpretations that can obfuscate public comprehension. The narrative surrounding the second cometary visitor exemplifies how complex astronomical information can be misconstrued and amplified through social media algorithms optimized for engagement rather than veracity. Differentiating between legitimate scientific breakthroughs and viral misinformation demands scrupulous attention to sources and context. The educational opportunities presented by Atlas facilitate astronomical outreach that bridges current research with fundamental inquiries about our cosmic standing. The object's interstellar origin offers tangible connections to concepts that might otherwise remain abstract. Public fascination with Atlas may influence funding priorities and mission planning for future interstellar object investigations, underscoring the value of maintaining capacities for studying these infrequent cosmic transients. Technological advancement. The examination of Atlas demonstrates how rapidly evolving technology augments our capacity to study faint, swiftly moving objects throughout the solar system. Each new technological capability unlocks further avenues for scientific exploration. Advanced detector technologies enable spectroscopic observations of objects too dim for preceding generations of instruments. These enhancements particularly benefit studies of distant, low-activity objects like Atlas during its inbound phase. Machine learning algorithms trained on extensive astronomical databases can discern subtle patterns and anomalies that human researchers might overlook. These tools prove exceptionally valuable for analyzing the intricate, rapidly evolving datasets generated by Atlas observations. Enhanced computational capacities facilitate sophisticated modeling of complex physical processes, enabling theoretical frameworks to keep pace with the increasingly detailed observational constraints provided by modern instruments. The integration of terrestrial and space-based observations creates synergistic capabilities that surpass the sum of individual contributions, permitting investigations impossible with any single observational platform. Future discoveries. The anomalous characteristics revealed by Atlas suggest that forthcoming interstellar visitors may exhibit equally surprising attributes that challenge our current understanding of these cosmic wanderers. Each new detection adds to our growing appreciation of their diversity. Advanced survey systems poised for activation will detect interstellar objects at considerably greater distances, affording extended lead times for detailed study and potentially enabling spacecraft interception missions with adequate advance warning. The expanding repository of data on interstellar objects will facilitate statistical studies that reveal patterns and correlations imperceptible in limited samples. These analyses may identify common characteristics or formation mechanisms applicable throughout our galaxy. Future space-based telescopes equipped with enhanced sensitivity and spectroscopic capabilities will permit detailed chemical analysis of interstellar objects, potentially uncovering isotopic signatures and exotic compounds that offer direct information regarding stellar nucleosynthesis processes. The evolution of rapid response spacecraft capabilities will revolutionize our ability to study interstellar objects in detail, enabling investigations that yield comprehensive understanding rather than the restricted snapshots possible with current remote observations. Galactic context. Atlas represents a single specimen from the immense population of minor bodies ejected from planetary systems throughout our galaxy's history. Comprehending its characteristics offers insights into planetary formation processes and stellar evolution across diverse galactic epochs. The estimated age of Atlas, potentially spanning billions of years, signifies its witness to galactic evolution over cosmologically significant timescales. Its composition preserves information about stellar nucleosynthesis and chemical conditions from earlier eras in our galaxy's history. Juxtaposing Atlas with other interstellar objects and solar system bodies reveals the variability of formation environments and evolutionary processes operative throughout our cosmic neighborhood. Each object embodies a unique experiment in planetary formation. Atlas's trajectory suggests an origin within the thick disk stellar population, furnishing our first direct sample of material from this ancient galactic component. Future investigations may ascertain whether thick disk objects exhibit systematically distinct compositions compared to their thin disk counterparts. Statistical models of galactic structure and stellar evolution incorporate data from interstellar objects to constrain theories concerning galactic chemical evolution and planetary system formation efficiency across varied stellar populations. Chemical clues. Each molecular species detected in Atlas provides constraints on the temperature, pressure, and chemical conditions present during its formation billions of years ago. The growing compendium of identified compounds establishes a profile of its formative environment. The unusual prevalence of carbon dioxide may indicate formation around stars with differing carbon-to-oxygen ratios than our Sun, possibly pointing to different stellar masses, evolutionary stages, or galactic chemical environments at the time the comet originated. The detection of organic compounds would furnish critical information regarding the prevalence of carbon chemistry in other stellar systems and potentially offer insights into the distribution of life's chemical precursors throughout our galaxy. Isotopic measurements, once successfully obtained, will provide direct constraints on nuclear processes within the parent star system, and serve as a test for models of stellar nucleosynthesis currently reliant entirely on astronomical observations and theoretical calculations. The temporal progression of Atlas's chemical signature as it approaches and recedes from the Sun illuminates how thermal processing affects interstellar material and provides insights into the physical structure and composition of its nucleus. Atmospheric interactions. As Atlas expels gas and dust into the surrounding space, complex interactions develop between its coma and the local electromagnetic environment. These processes give rise to observable phenomena that offer supplementary diagnostic tools for comprehending the comet's behavior and composition. The solar wind, carrying embedded magnetic fields and charged particles, encounters the neutral gases surrounding Atlas, initiating chemical reactions that generate ionized species detectable through characteristic emission lines. These interactions foster a secondary chemistry distinct from the sublimation processes occurring at the nuclear surface. Ultraviolet radiation emanating from the Sun photodissociates molecular species within the coma, breaking apart complex compounds and generating fragments that may not exist under terrestrial conditions. This photochemistry produces short-lived species that are challenging to detect but yield crucial information about the parent molecules from which they are derived. Upcoming observations of Atlas by the Parker Solar Probe will occur within the solar wind environment where these interactions reach their zenith. The spacecraft's plasma instruments may detect perturbations in the solar wind caused by the comet's passage, revealing information about outgassing rates and coma composition that is invisible to remote sensing. Magnetohydrodynamic simulations model the intricate interactions between the solar wind, interplanetary magnetic field, and Atlas's expanding coma to elucidate the underlying physics. These calculations necessitate sophisticated numerical methodologies and extensive computational resources to accurately capture the relevant physical processes. Dust properties investigation. The anomalous polarization characteristics of Atlas suggest that its dust particles possess properties significantly divergent from those found in solar system comets. Understanding these distinctions offers insights into processes occurring in other stellar systems. Light scattering measurements aim to ascertain particle size distributions, refractive indices, and morphologies that govern Atlas's interaction with solar radiation. The observed deep negative polarization indicates particles with distinctive optical attributes that may reflect exotic compositions or unusual structures. Laboratory experiments employing analog materials aid in interpreting polarization measurements by providing controlled studies of how different particle compositions and structures influence light scattering properties. These experiments demonstrate that the observed polarization signature necessitates either unconventional compositions or particle morphologies atypical of terrestrial materials. Advanced electromagnetic scattering calculations model various particle compositions, sizes, and shapes to align with observed polarization and brightness measurements. These models suggest that Atlas may eject particles with complex internal structures or surface properties indicative of formation within different chemical environments. The temporal evolution of polarization properties as Atlas approaches perihelion may reveal modifications in particle characteristics caused by thermal processing or the activation of distinct outgassing sources within the nucleus. Such an evolution would offer unique insights into how solar heating impacts interstellar material. Fragmentation dynamics. The intense thermal stresses experienced during perihelion passage pose significant risks of nuclear fragmentation, which could fundamentally alter Atlas's subsequent trajectory. Historical observations of cometary fragmentation events provide context for assessing this possibility. Cycles of thermal expansion and contraction can induce internal fractures, weakening the nuclear structure and rendering it more susceptible to disruption from gas pressure or rotational forces. The porous, heterogeneous structure typical of cometary nuclei makes them particularly vulnerable to thermal stress fracturing. Sublimation pressure from trapped gases within the nucleus can exceed the mechanical integrity of the surrounding material, leading to explosive outgassing events that fragment portions of the nucleus. Such occurrences often manifest as dramatic increases in brightness followed by the appearance of multiple components in high-resolution imagery. Monitoring Atlas for indications of fragmentation requires high angular resolution imaging capable of detecting small fragments separating from the main nucleus. The Hubble Space Telescope provides the foremost observational capability for such studies, although the comet's solar position limits observational opportunities during its period of highest fragmentation risk. Mathematical models of nuclear structure and thermal evolution attempt to predict fragmentation probabilities based on estimated composition, porosity, and mechanical properties. These models incorporate laboratory measurements of ice mechanical properties and thermal expansion coefficients under space conditions. Comparative analysis. A detailed comparison between Atlas and the two previously observed interstellar objects reveals both similarities and critical divergences that illuminate the diversity of these cosmic visitors. Each object represents a unique sample originating from disparate stellar environments and developmental histories. Oumuamua exhibited no detectable outgassing despite displaying non-gravitational acceleration, suggesting either a very low volatile content or unusual physical properties that precluded gas detection. Its elongated form and rapid rotation presented challenges for theoretical interpretation that remain unresolved. Boris appeared more analogous to typical solar system comets, with clearly detectable water vapor and dust emissions that adhered to expected patterns of increasing solar heating. However, its chemical composition presented subtle differences indicative of formation within a different stellar environment. Atlas integrates characteristics from both prior visitors while exhibiting unique features not observed in either predecessor. Its early activity, unusual chemical composition, rapid brightening, and anomalous morphology establish a distinctive profile that broadens our understanding of interstellar object diversity. Statistical analysis of the limited sample of known interstellar objects suggests that each represents a distinct class or formation environment, implying immense variability within the population of objects traversing interstellar space. Forthcoming detections will ascertain whether this apparent diversity reflects true population characteristics or biases introduced by observational selection. The accumulating data from multiple interstellar objects facilitate comparative studies that may reveal common formation mechanisms or evolutionary processes, while highlighting the unique attributes that distinguish objects originating from different stellar systems. Nucleus modeling. Comprehending the internal structure and composition of Atlas necessitates sophisticated theoretical models that integrate observational constraints while acknowledging the inherent fundamental uncertainties associated with studying such distant, diminutive objects. Thermal models strive to replicate observed outgassing patterns by varying nucleus composition, porosity, thermal conductivity, and structural attributes. These models demonstrate that multiple parameter combinations can produce similar observational signatures, underscoring the challenges of uniquely determining internal properties. The premature onset of activity suggests either a very high volatile content or enhanced heat transfer mechanisms that permit solar heating to penetrate deeply into the nucleus, even at considerable distances from the Sun. Such characteristics might reflect formative conditions or structural modifications sustained during interstellar transit. Sophisticated models, incorporating various layers within the nucleus, strive to elucidate the intricate temporal progression of Atlas's activity. These theoretical frameworks propose that thermal penetration progressively awakens distinct chemical reserves as the celestial body draws nearer to perihelion. Advanced computational methodologies facilitate the three-dimensional mapping of nuclear structure, accounting for realistic heterogeneity, porosity fluctuations, and intricate chemical distributions. These simulations necessitate considerable computational resources but yield detailed projections for comparison with empirical observations. The velocity assessment. The extraordinary velocity of Atlas in relation to our solar system offers vital insights into its origins and developmental trajectory. Objects expelled from nearby stellar systems are expected to exhibit velocities correlated with the kinematics of their parent stars and the effectiveness of the expulsion mechanisms. Stellar encounter simulations endeavor to replicate Atlas's observed velocity through gravitational interactions with massive celestial bodies during its interstellar voyage. These calculations indicate that numerous stellar encounters could alter the initial ejection velocity and complicate efforts to pinpoint the originating system. The alignment of Atlas's path with the galactic plane suggests a potential origin within the thick disk stellar population, which displays different kinematic traits compared to the thin disk region where our Sun is situated. This alignment provides statistical constraints on probable areas of origin. Galactic orbit calculations trace Atlas's movement through the galaxy's gravitational field over millions of years, factoring in the complex dynamics of stellar systems embedded within the galactic potential. These computations reveal probable trajectories and highlight regions where the comet might have originated. The high velocity also implies that Atlas will depart our solar system with considerable kinetic energy, propelling it into interstellar space, where it may eventually encounter other star systems and potentially influence their chemical development through cross-contamination. The observational obstacles. The investigation of Atlas presents numerous technical hurdles that push the boundaries of current observational capacities. The combination of faintness, rapid motion, and limited observational periods demands inventive strategies and meticulous coordination among multiple observatories. Tracking swift-moving objects necessitates sophisticated telescope guidance systems capable of precisely following predicted paths while maintaining accurate pointing for extended spectroscopic exposures. Minor inaccuracies in orbital projections can lead to the target moving beyond the telescope's field of view during prolonged observations. Atmospheric turbulence particularly impacts the observation of faint, distant objects like Atlas, requiring exceptional seeing conditions or adaptive optic systems to achieve the resolution necessary for detailed morphological studies. Many planned observations are contingent on favorable meteorological conditions, which cannot be guaranteed. The comet's position relative to the Sun introduces further complications, with solar conjunction rendering ground-based observations impossible during the most scientifically significant periods surrounding the event. Space-based observatories become indispensable for maintaining observational coverage during this critical phase. Coordinating observations among multiple facilities across different time zones requires meticulous scheduling and communication to ensure efficient data acquisition. Despite potential equipment malfunctions, weather-related delays, or other unforeseen issues that commonly affect astronomical operations. The spectroscopic techniques. Advanced spectroscopic analysis of Atlas requires sophisticated methods capable of extracting weak signals from complex backgrounds while accounting for the comet's swift movement and fluctuating observational circumstances. High-resolution spectroscopy aims to resolve individual emission lines from various molecular constituents, enabling precise velocity determinations and abundance measurements that constrain models of coma chemistry and dynamics. Such observations necessitate large telescopes and prolonged exposure times. Multi-wavelength spectroscopy, spanning ultraviolet, visible, and infrared spectrums, provides comprehensive coverage of diverse molecular transitions and electronic states. Each wavelength range offers unique diagnostic capabilities for identifying specific chemical species and physical conditions. Doppler shift measurements of emission lines reveal gas expansion velocities and outflow patterns within the coma, offering insights into the physical processes driving outgassing and the structural characteristics of the nucleus. These measurements demand exceptionally precise wavelength calibration. Time-resolved spectroscopy tracks rapid alterations in emission line intensities and ratios that may signify variable outgassing, chemical reactions, or structural modifications within the nucleus. Such observations require continuous monitoring over extended durations with consistent instrumental configurations. Polarization spectroscopy examines how the polarization state of emission lines varies with observational geometry and molecular attributes, providing supplementary constraints on physical conditions and chemical processes that complement intensity measurements. The chemical evolution. The evolving chemical signature of Atlas as it approaches perihelion offers real-time insights into how thermal processes activate previously dormant chemical reserves within the nucleus. The emission of carbon dioxide is progressively augmented by additional molecular species as escalating solar heating penetrates deeper into the nucleus, activating more volatile components. This progression elucidates the chemical stratification within the nucleus and demonstrates how changing thermal conditions stimulate new chemistry. The steep power law dependency on solar distance suggests either unusual chemical kinetics or structural properties that amplify thermal impacts. The detection of organic molecules becomes increasingly probable as thermal processing breaks down complex compounds, releasing simpler fragments detectable through characteristic emission signatures. Such discoveries would furnish crucial information concerning carbon chemistry and other stellar systems. The temporal sequence of chemical activation may reveal insights into nuclear structure and formation history, with different chemical reserves becoming accessible as thermal penetration reaches varied depths within the heterogeneous nucleus. Comprehending how Atlas's chemistry evolves into its outbound phase will provide insights into how thermal cycling affects materials formed in other stellar systems and may unveil chemical processes unique to interstellar environments. The particle acceleration. The anomalous sunward extension of scattered light around Atlas suggests particle acceleration or transport mechanisms that diverge from typical cometary processes. Understanding these mechanisms necessitates a detailed examination of particle dynamics within the complex electromagnetic environment surrounding the comet. Radiation pressure from solar photons typically propels dust particles away from the Sun, forming the familiar antisolar tail structure observed in most comets. The apparent reversal of this effect in Atlas challenges our comprehension of particle physics in cometary settings. Electromagnetic interactions involving charged dust grains and the interplanetary magnetic field could potentially create unusual particle trajectories, contributing to the observed sunward extension. Such effects are contingent on particle size, charge state, and local magnetic field conditions. Gas drag forces from expanding neutral gases in the coma can influence particle motion, particularly for minute grains that couple efficiently with gas flows. Intricate gas dynamics driven by non-uniform outgassing could generate particle transport patterns differing from simple radiation pressure acceleration. Electrostatic charging of dust particles in the solar wind environment generates additional forces that may contribute to aberrant particle trajectories. The equilibrium between gravitational, electromagnetic, and radiation pressure forces dictates particle movement and observable signatures. Advanced particle dynamics simulations, incorporating realistic electromagnetic environments and complex outgassing patterns attempt to replicate the observed morphological features and elucidate the underlying physical processes responsible for the anomalous sunward extension. The thermal penetration. Solar heating of Atlas creates temperature gradients within the nucleus, driving sublimation and outgassing at various depths beneath the surface. Understanding these thermal processes requires detailed modeling of heat transfer through porous, heterogeneous materials under space conditions. Thermal diffusion calculations predict how solar heating penetrates the nucleus as a function of thermal conductivity, porosity, and composition. These models reveal that typical cometary materials require substantial solar heating before internal temperatures reach sublimation thresholds for common ices. The early activity observed in Atlas suggests either unusually efficient heat transfer or a composition dominated by species that sublimate at lower temperatures than water ice. Carbon dioxide and carbon monoxide both sublimate at temperatures well below water, potentially accounting for the early onset of activity. Thermal modeling must account for the complex feedback between sublimation and heat transfer, as gas production removes latent heat while simultaneously creating pathways for enhanced thermal conduction. These coupled processes result in nonlinear behavior that complicates theoretical analysis. Subsurface temperature monitoring through thermal emission measurements provides observational constraints for thermal models and aids in distinguishing between different scenarios for nuclear structure and composition. Such observations require sensitive infrared instruments and careful subtraction of reflected sunlight. The thermal evolution of Atlas through its perihelion passage will test theoretical models and may reveal thermal behavior unique to interstellar objects possessing different formation histories and structural characteristics compared to solar system comets. The rotation. Measuring Atlas's rotation period presents significant observational challenges due to its diminutive size, considerable distance, and low amplitude brightness variations. Nevertheless, successful determination of its rotation would furnish crucial information regarding nuclear shape, density distribution, and structural integrity. Photometric monitoring aims to detect periodic brightness fluctuations caused by the rotation of an irregularly shaped nucleus or heterogeneous surface composition. Such variations typically yield amplitude changes of only a few percent, necessitating precise measurements over extended periods. The rotation period influences how solar heating is distributed across the nuclear surface, impacting outgassing patterns and potentially generating observable asymmetries in the coma or tail structure. Understanding rotational effects aids in interpreting morphological features. Rapid rotation can induce centrifugal stresses that exceed the mechanical strength of loosely bound cometary material, potentially leading to mass shedding or structural failure. Conversely, slow rotation may indicate either high density or significant internal cohesion. Non-principal axis rotation, common among small solar system bodies, generates complex photometric signatures that require sophisticated analytical techniques to extract meaningful physical parameters. Such rotational states may arise from prior fragmentation events or asymmetric outgassing torques. Successful rotation determination for Atlas would represent the first such measurement for an interstellar object, enabling comparison with the rotational properties of solar system comets to ascertain whether formation in different stellar environments produces objects with distinct rotational characteristics. The contamination assessment. The passage of Atlas through our solar system prompts questions regarding contamination exchange between interstellar objects and our local environment. Understanding these processes has implications for astrobiology and the chemical evolution of planetary systems. Solar wind particles, carrying isotopic signatures characteristic of our Sun, may become incorporated into Atlas's surface or coma, leading to contamination that could complicate future chemical analyses. The efficacy of such processes depends on interaction cross-sections and resonance times. Interplanetary dust grains originating from solar system sources may collide with Atlas during its passage, embedding foreign material that alters surface composition and potentially influences subsequent outgassing behavior. Such contamination could yield misleading chemical interpretations. Conversely, Atlas expels material into interplanetary space, which may eventually be incorporated into solar system bodies or collected by future sample return missions. This material carries chemical signatures from other stellar systems and represents a form of natural cross-contamination between star systems. Atmospheric escape from Earth and other planets contributes trace amounts of planetary material to interplanetary space, some of which may be collected by passing interstellar objects. Although extremely dilute, Such contamination provides a mechanism for transferring planetary signatures across interstellar distances. Understanding contamination processes aids in assessing the pristine nature of interstellar objects and guides the interpretation of chemical analyses that may detect unexpected signatures resulting from contamination rather than intrinsic composition. The mission architecture. Future dedicated missions to study interstellar objects necessitate innovative spacecraft designs and mission architectures capable of accommodating the rapid response timelines and extreme velocity requirements imposed by these transient visitors to our solar system. Rapid launch capabilities demand pre-positioned spacecraft or advanced propulsion systems that can achieve the velocity changes required to intercept fast-moving interstellar objects. Conventional chemical propulsion proves inadequate for most intercept scenarios without unrealistic propellant demands. Solar sail technology offers potential advantages for interstellar object missions, providing continuous acceleration without propellant consumption and enabling trajectory adjustments post-launch. However, solar sails require large surface areas and sophisticated attitude control systems. Nuclear propulsion concepts under development could provide the high specific impulse necessary for ambitious interstellar object missions, including potential sample return capabilities that would revolutionize our understanding of these cosmic visitors. Such systems require substantial technological development and testing. Mission designs must accommodate the limited warning time available when interstellar objects are detected, requiring pre-approved mission concepts, standby spacecraft, and streamlined decision-making processes that can be rapidly enacted. Structure determination and potentially returning samples from other stellar systems to Earth-based laboratories. The database development. Each interstellar object detection contributes valuable data to an expanding database, which will eventually facilitate statistical studies of these cosmic wanderers and their relationship to galactic structure and stellar evolution processes. Standardized data formats and analysis procedures ensure that observations from different observatories and time periods can be effectively combined for comparative studies and population analysis. Such standards necessitate coordination among international astronomical organizations. The accumulating database will eventually reveal correlations between object characteristics and trajectory properties that may indicate common formation mechanisms or evolutionary processes operating throughout our galactic neighborhood. Machine learning algorithms, trained on extensive datasets, may identify subtle patterns and relationships that elude traditional statistical analysis, potentially unveiling new categories of interstellar objects or unexpected correlations between observable properties. Long-term database maintenance requires careful curation and quality control to ensure data remains accessible and useful for future researchers employing analytical techniques yet to be developed. Archival standards must anticipate technological evolution and evolving research needs. The database will serve as a crucial resource for planning future observations and missions, enabling researchers to identify knowledge gaps and prioritize investigations that will maximize scientific return from limited observational opportunities. The theoretical advances. The unusual characteristics of Atlas are driving advancements in the theoretical understanding of cometary physics, dust dynamics, and thermal processes, which will benefit studies of both interstellar and solar system objects. Multi-phase physics and three-dimensional structures are being developed to explain the full spectrum of observed phenomena. These models necessitate sophisticated numerical techniques and substantial computational resources. New theoretical frameworks for understanding particle acceleration and transport in cometary environments are emerging to explain the unusual morphological features observed in Atlas. These frameworks may be applicable to other astronomical contexts involving dust and gas interactions. Improved models of thermal processes in heterogeneous porous materials are being developed to comprehend how solar heating affects objects with different formation histories and structural characteristics than typical solar system bodies. The integration of observational constraints with theoretical predictions creates feedback loops that refine our understanding of fundamental physical processes while highlighting areas where current models remain incomplete or inaccurate. These theoretical advancements will enhance our ability to interpret observations of future interstellar objects and may reveal universal principles applicable to small body physics throughout the galaxy. The detection evolution. The discovery of Atlas exemplifies how modern survey capabilities have revolutionized our capacity to detect and study interstellar objects, while also pointing toward even more significant improvements anticipated from next-generation facilities. Current surveys achieve detection rates limited by telescope aperture, detector sensitivity, and data processing capabilities. Upcoming facilities will enhance all these factors, dramatically increasing the discovery rate for interstellar objects. The Verisi Rubin Observatory, scheduled to commence operations shortly, will survey the entire visible sky every few nights with unprecedented sensitivity, potentially detecting dozens of interstellar objects annually once fully operational. Advanced data processing algorithms incorporating machine learning and artificial intelligence will enable real-time identification of moving objects and rapid classification of their orbital characteristics, accelerating the time frame between detection and follow-up observations. Space-based survey systems currently under development will offer continuous monitoring capabilities unaffected by weather, atmospheric turbulence, or daylight constraints that limit ground-based observations. Such systems could detect interstellar objects at much greater distances. The transition from detecting a few interstellar objects per decade to potentially dozens per year will transform our understanding of these cosmic visitors from studies of individual anomalies to statistical analyses of representative populations. The international cooperation. The examination of Atlas serves as a prime illustration of how contemporary astronomical pursuits necessitate global collaboration to achieve maximum scientific yield from fleeting observational windows. Coordinated endeavors, extending across multiple continents and organizations, prove indispensable for comprehensive understanding. The disparities in time zones facilitate continuous surveillance as celestial bodies traverse the sky, with observations being seamlessly transferred between facilities as Earth's rotation positions various telescopes advantageously. Such intricate coordination demands meticulous planning and dependable communication infrastructure. The pooling of resources grants access to specialized instruments and methodologies that no single entity could independently sustain. International alliances enable investigations that would otherwise be beyond the reach of any individual organization. Uniform standards for data exchange and interpretation foster swift teamwork among research collectives worldwide, paving the way for exhaustive studies that integrate varied observational viewpoints and analytical approaches. The triumph of international cooperation in unraveling the mysteries of Atlas establishes foundational models for probing future interstellar entities and underscores the advantages of harmonized astronomical research in tackling formidable scientific queries. Subsequent explorations of interstellar objects will benefit from the collaborative structures forged during Atlas's observations, promoting more effective utilization of Earth's astronomical assets and optimizing the scientific returns from these infrequent cosmic encounters. The educational ramifications are also noteworthy. The discovery and subsequent investigation of Atlas present unparalleled avenues for public enlightenment and outreach, forging connections between present-day scientific endeavors and the vast cosmos, alongside the fundamental nature of cosmic development. The interstellar lineage of Atlas ignites public fascination in ways that typical astronomical findings seldom achieve, offering natural entry points for discussions on stellar evolution, galactic architecture, and the mechanisms that sculpt our cosmic environment. Real-time observational data empowers educational initiatives that track scientific investigations as they unfold, demonstrating the practical progression of astronomical research and highlighting both the thrill and the challenges inherent in pioneering science. The interdisciplinary character of Atlas studies showcases the integration of physics, chemistry, geology, and computer science within modern astronomy to address intricate scientific questions demanding diverse expertise and analytical prowess. Educational materials crafted for Atlas outreach will serve as valuable resources for disseminating knowledge about these celestial visitors and their scientific importance in comprehending galactic evolution. The worldwide scope of Atlas observations demonstrates how international scientific partnership addresses questions that transcend geopolitical borders and call for cooperative strategies that reflect the universal spirit of scientific inquiry. The future implications are profound. The study of Atlas signifies merely the dawn of a new epoch in the exploration of interstellar objects, an epoch poised to dramatically enhance our grasp of galactic structure, stellar evolution, and the myriad forms of planetary formation processes across the cosmos. Enhanced detection capabilities will ascertain whether Atlas represents a typical interstellar traveler or an atypical specimen that serendipitously captured our attention. The genuine diversity of these objects remains largely unexplored. Dedicated missions focused on studying interstellar objects in depth will yield comprehensive insights that, while complementing, will far surpass the information obtainable from remote observations alone. Such missions hold the potential to reveal entirely unexpected characteristics imperceptible from Earth-based perspectives. Small samples could ultimately lead to the identification of formation mechanisms and evolutionary pathways within distant galaxies. Extended monitoring of interstellar object detection rates and characteristics will provide valuable perspectives on galactic evolution, the efficiency of stellar system formation, and the processes governing the exchange of material between disparate regions of our cosmic neighborhood. The methodologies developed for studying Atlas will prove beneficial in investigating solar system objects, enabling more granular characterization of comets, asteroids, and other minor bodies that hold preserved information regarding the formation and evolution of our own planetary systems. The quantum mechanical underpinnings. At the molecular scale, Atlas exhibits quantum mechanical processes that dictate how absorbed solar energy fuels chemical transformations and phase transitions within its nucleus. Comprehending these fundamental mechanisms necessitates sophisticated theoretical frameworks that bridge quantum chemistry and macroscopic thermodynamics. Photodissociation of molecular species within the coma transpires when ultraviolet photons possess sufficient energy to rupture chemical bonds, generating reactive fragments that may reassemble into novel compounds or disperse into space. These quantum phenomena dictate which molecules endure long enough for spectroscopic identification. Electronic excitation states within various molecular species give rise to the distinctive emission lines observed in Atlas's spectrum. Each transition corresponds to specific quantum energy levels contingent upon molecular architecture and ambient conditions within the coma. Vibrational and rotational quantum states of molecules furnish supplementary spectroscopic indicators that reveal temperature, density, and chemical composition within distinct sectors of the expanding coma. These quantum signatures enable remote determination of physical parameters that are otherwise unmeasurable directly. Quantum tunneling effects in chemical reactions become significant at the frigid temperatures characteristic of cometary nuclei, potentially facilitating chemical processes that would be prescribed under classical thermodynamic principles. Such effects may contribute to the anomalous chemistry observed in Atlas. The quantum mechanical nature of photon interactions with matter governs absorption and emission efficiencies, which in turn regulate the heating of the nucleus by solar radiation and the expulsion of volatiles. Understanding these interactions requires meticulous quantum calculations for intricate molecular systems. The hydrodynamic dynamics. The outward expansion of gas and dust from the nucleus of Atlas engenders complex hydrodynamic flows that dictate coma structure, particle dispersal, and observable morphological features. These phenomena necessitate sophisticated fluid dynamics modeling that accounts for multi-component flows and fluctuating thermodynamic conditions. Gas expansion originating from localized emission sources on the nucleus's surface generates jets and collimated outflows that interact with the surrounding coma environment through shock formation, turbulent mixing, and momentum transfer processes. These interactions shape the overall coma morphology and particle distribution. The entrainment of dust grains within expanding gas streams is contingent upon particle size, gas density, and localized velocity gradients that vary across the coma. Smaller particles couple efficiently with gas motion, whereas larger grains follow more independent trajectories governed by gravitational and radiation pressure forces. Non-equilibrium thermodynamics characterize conditions within the expanding coma, where distinct molecular species may exhibit independent temperature and velocity distributions that evolve as the gas expands and cools. These conditions influence chemical reaction rates and spectroscopic signatures. Computational fluid dynamics simulations integrate realistic nucleus geometry, heterogeneous outgassing sources, and multi-species chemistry to predict observable coma characteristics. These calculations demand substantial computational resources and sophisticated numerical methods to accurately represent the relevant physical processes. The anomalous morphological features observed in Atlas, particularly the sunward extension of scattered light, challenge current hydrodynamic models and may necessitate novel theoretical frameworks incorporating exotic physics or unusual boundary conditions. The magnetic field interactions. Atlas's passage through the heliosphere exposes it to intricate magnetic field environments that influence the motion of charged particles, plasma chemistry, and electromagnetic signatures detectable by sensitive instrumentation. These interactions offer additional diagnostic tools for comprehending the comet's behavior. The interplanetary magnetic field, embedded within the solar wind, establishes preferred pathways for charged particle trajectories, potentially contributing to asymmetric coma structures or directional outflow patterns. Such effects are dependent on the local magnetic field's orientation and intensity at Atlas's location. Photoionization of neutral species within the coma generates charged particles that respond to electromagnetic forces differently than their neutral counterparts. These ions follow complex paths dictated by the equilibrium between gravitational, electric, and magnetic forces. Magnetic reconnection events within the solar wind environment can create localized acceleration zones that impact charged particles in the vicinity of Atlas, potentially contributing to unusual particle signatures or electromagnetic emissions detectable by radio telescopes. Plasma instabilities, induced by the interaction between the solar wind and Atlas's ionosphere, can generate electromagnetic waves detectable at radio frequencies. Such emissions would furnish information regarding plasma conditions and magnetic field configurations near the comet. Advanced magnetohydrodynamic simulations model the intricate interactions between Atlas's expanding coma and the magnetized solar wind environment to predict observable electromagnetic signatures and elucidate the underlying physics of these interactions. The isotopic signatures. Future high-resolution spectroscopic observations may ultimately ascertain isotopic ratios within Atlas, providing direct insights into nuclear processes within its parent star system and constraining models of stellar nucleosynthesis and galactic chemical evolution. Carbon isotope ratios reflect the balance between different nuclear fusion processes in the parent star, with carbon-12 to carbon-13 ratios serving as indicators of stellar mass, evolutionary phase, and metallicity. These measurements necessitate exceptionally high signal-to-noise ratios. Oxygen isotope signatures offer information regarding stellar nucleosynthesis pathways and potential contamination from supernovae in the stellar environment where Atlas originated. Variations in isotopic ratios signify formation around stars with differing masses and evolutionary histories. Nitrogen isotope measurements help constrain models of stellar evolution and galactic chemical evolution by revealing the efficiency of nitrogen production in diverse stellar environments. These signatures preserve information about conditions billions of years ago when Atlas coalesced. Deuterium to hydrogen ratios provide insights into primordial nucleosynthesis and subsequent chemical processing in interstellar and stellar environments. Such measurements, while pushing the boundaries of current observational capabilities, would offer unique constraints on cosmological and galactic evolution models. The technical challenges associated with isotopic measurements from such distant and faint celestial bodies demand next-generation instruments with unparalleled sensitivity and spectral resolution. Future space-based observatories may eventually possess the capabilities required for detailed isotopic analysis. The chemical network modeling. The intricate chemistry occurring within Atlas's coma involves hundreds of potential reactions among various molecular species, ions, and radicals generated by solar radiation and electron impact processes. Understanding this complex chemistry requires sophisticated network models that meticulously track all relevant species and reactions. Gas phase chemistry in the coma operates under conditions far removed from thermodynamic equilibrium, with reaction rates governed by radiation fields, temperature gradients, and density variations that continuously shift as the coma expands and evolves. Photochemical models incorporate detailed cross-sections for photodissociation, photoionization, and electronic excitation processes that determine how solar ultraviolet radiation drives chemical reactions and produces observable emission signals. Electron impact chemistry becomes significant in regions where photoionization creates substantial electron populations capable of driving additional chemical reactions through collisional processes. These reactions may yield species not generated through photochemical pathways alone. Surface chemistry on dust grains provides additional reaction pathways that could be particularly crucial for forming complex organic molecules via heterogeneous catalysis. Such processes might produce chemical signatures distinct from purely gas-phase chemistry. Chemical network calculations predict the abundances of hundreds of molecular species and their temporal and spatial evolution within the coma. These models facilitate the interpretation of spectroscopic observations and guide the search for novel molecular signatures. The formation scenarios. Atlas's composition and trajectory provide crucial constraints for theoretical models of its origin environment and evolutionary history, offering insights into planetary system formation processes around diverse stellar types throughout galactic history. Formation within a metal-poor star in the galactic thick disk could account for its unusual chemical composition, with distinct stellar nucleosynthesis products leading to unique ice compositions not found in our solar system's formation environment. Alternative formation scenarios involve the capture of interstellar material during passage through dense molecular clouds, potentially explaining anomalous isotopic signatures or chemical compositions reflecting interstellar rather than stellar system processing. Collisional fragmentation of larger bodies within the parent planetary system could produce objects with peculiar structural characteristics or chemical distributions that influence subsequent outgassing behavior and observational properties. Late-stage thermal processing within the parent system might have altered the original composition through sublimation and reaction processes, creating the layered structure suggested by Atlas's complex activity patterns. Tidal disruption during ejection from the parent system could have resulted in internal fractures or structural modifications affecting thermal conduction and outgassing efficiency in ways that differentiate interstellar objects from solar system comets. Each formation scenario predicts different observable characteristics that can be tested through ongoing observations and theoretical modeling, potentially enabling the determination of Atlas's true origin and evolutionary trajectory. The galactic archaeology. Atlas represents a direct sample of material originating from distant regions of our galaxy, potentially preserving chemical signatures from stellar environments that no longer exist or have undergone significant evolution since the comet's formation billions of years ago. The suggested origin in the thick disk, inferred from Atlas's trajectory, indicates formation around ancient stars that existed when the galaxy possessed a different chemical composition and structure than it does today. Such objects offer unique perspectives into galactic evolution across cosmic timescales. Chemical signatures preserved within Atlas may reveal information about stellar nucleosynthesis processes in early galactic history, when metallicity was lower and stellar populations differed significantly from those present in our current galactic neighborhood. Comparative studies of multiple interstellar objects from disparate galactic regions and evolutionary epochs will eventually enable the mapping of chemical evolution throughout our galaxy's history, providing observational validation for theoretical models of galactic formation and evolution. The preservation of ancient chemical signatures depends on the thermal and radiation environment experienced during Atlas's interstellar journey, with cosmic ray bombardment and occasional stellar encounters potentially altering surface composition over millions of years. Future investigations of Atlas and similar objects will contribute to the burgeoning field of galactic archaeology, utilizing minor bodies as time capsules preserving information about cosmic chemical evolution over billions of years. The astrobiological implications. While Atlas exhibits no overt signs of biological activity, its study offers insights into the prevalence of organic chemistry throughout our galaxy and the potential for life-supporting materials to traverse between stellar systems. The detection of organic compounds within Atlas would demonstrate that carbon chemistry capable of underpinning biological processes exists in other stellar systems, potentially indicating a widespread distribution of life's chemical precursors throughout our galaxy. Interstellar panspermia scenarios posit that life-bearing materials could travel between star systems via objects like Atlas. However, the extreme conditions of interstellar space render the survival of complex biological systems highly improbable over multi-million-year timescales. The observed chemical diversity in Atlas and other interstellar objects suggests that planetary systems throughout our galaxy may have access to chemical inventories significantly different from those available during Earth's formation, potentially leading to exotic biochemistries. Contamination studies reveal how materials are exchanged between stellar systems through interstellar visitors, creating natural experiments in chemical transport that may influence the development of life in recipient planetary systems. Future missions focused on interstellar objects, equipped with enhanced biological detection capabilities, may search for organic signatures or even preserved biological materials, which could revolutionize our understanding of life's distribution throughout the cosmos. The observational legacy. The extensive observational campaign dedicated to Atlas has established new paradigms for the study of transient astronomical phenomena and generated data sets that will support research for decades to come. The development of an archival system ensures that Atlas observations remain accessible to future researchers employing analysis techniques yet to be invented, maximizing the long-term scientific returns from this unparalleled opportunity to study an interstellar visitor. Methodological advancements developed for Atlas observations will benefit studies of future interstellar objects, solar system comets, and other astronomical phenomena requiring rapid response capabilities and coordinated multi-facility campaigns. The involvement of amateur astronomers highlights the value of citizen science networks for monitoring rapidly evolving phenomena and underscores the importance of maintaining diverse observational capacities. Data analysis techniques pioneered for Atlas will find applications in other areas of astronomy where similar challenges arise in studying faint, rapidly moving objects with complex temporal evolution. The collaborative frameworks established during Atlas observations provide blueprints for future international astronomical projects that necessitate coordination among diverse institutions and rapid sharing of time-critical information. The technological innovations. The study of Atlas has spurred innovation in observational techniques, data analysis methodologies, and theoretical modeling approaches, thereby advancing the broader capabilities of astronomical research. Advanced image processing algorithms developed to extract faint signals from Atlas observations will benefit studies of other dim astronomical objects where traditional techniques prove insufficient. Machine learning applications for automated detection and classification of moving objects have been refined through Atlas observations, enhancing our ability to identify and characterize future interstellar visitors. Spectroscopic techniques optimized for rapid cadence observations of faint objects enable novel approaches to studying variable astronomical phenomena across diverse fields of astronomy. Advancements in computational simulations, spurred by the necessity to comprehend the peculiar attributes of Atlas, will undoubtedly enhance the foundational theories employed in investigating cometary physics, the behavior of particulate matter, and the thermal dynamics of smaller celestial bodies. Space-based observational techniques have been refined through the analysis of ATLAS, leading to more effective strategies for conducting synchronized astronomical missions. The phenomenon of ATLAS has captivated the public's imagination to an extraordinary degree, forging opportunities for scientific exploration, communication, and instruction that address fundamental inquiries regarding our celestial origins. Engagement across social media platforms illustrates both the potential and the difficulties inherent in conveying intricate scientific findings to a broad spectrum of individuals, underscoring the critical need for reliable sources of information and lucid explanations of uncertainties and limitations. Educational initiatives, conceived around the observations of ATLAS, offer tangible, real-time illustrations of the scientific research process, showcasing both the thrill of discovery and the rigorous methodologies essential for obtaining dependable outcomes. The international collaborative nature of ATLAS studies exemplifies how contemporary astronomy transcends national borders and represents a unified human endeavor to comprehend our position within the cosmos. Maintaining public fascination with astronomical research is paramount. The investigation of ATLAS integrates a wide array of scientific disciplines and analytical methodologies to tackle complex questions that necessitate extensive expertise. Future discoveries await. ATLAS serves as a precursor to next-generation survey systems, which are projected to detect numerous interstellar objects each year. This will facilitate statistical analyses that reveal characteristics of their populations and mechanisms of formation that are currently obscured within limited sample sizes. The deployment of specialized spacecraft missions designed to intercept and examine interstellar objects will yield detailed insights unattainable through remote sensing, potentially uncovering entirely unforeseen properties and challenging existing theoretical constructs. Such missions will enable comparative studies that pinpoint patterns and correlations across diverse galactic settings and historical epochs of cosmic evolution. Sophisticated analytical techniques will be instrumental in extracting increasingly granular information from both current and prospective observations, thereby unveiling subtle indicators of formation conditions and evolutionary trajectories. The study of interstellar objects is poised to transition from merely characterizing individual curiosities to undertaking comprehensive surveys that map the variability of planetary formation outcomes throughout our galaxy. This represents a scientific revolution. The identification and study of interstellar objects like ATLAS signify a fundamental paradigm shift in astronomy, granting humanity direct access to materials originating from other stellar systems for the first time in our history. This revolution mirrors other transformative leaps in astronomical understanding that have broadened our cosmic perspective. From the initial realization that stars are essentially distant suns to the subsequent discovery of exoplanets orbiting other stars, the capacity to directly examine materials from other stellar systems challenges established theoretical models and provides observational tests previously unimaginable, potentially revolutionizing our comprehension of planetary formation and stellar evolution. Subsequent advancements in the detection and characterization of interstellar objects will accelerate this transformative period, delivering progressively detailed intelligence about cosmic environments across our galactic neighborhood. The implications of this research extend beyond astronomy into fields such as planetary science, astrobiology, and cosmology, fostering interdisciplinary investigations that address fundamental questions concerning the evolution of the universe. This ongoing scientific revolution will continue to expand human knowledge and perspective, establishing direct links to cosmic environments that existed billions of years ago and are trillions of kilometers away. The cosmic perspective embodied by ATLAS underscores the profound interconnectedness of celestial systems, illustrating the flow of matter and information between stellar systems across immense distances and timeframes that dwarf human experience. The realization that we exist within a dynamic galactic ecosystem, wherein objects regularly traverse between star systems, fundamentally reshapes our perception of Earth's place in the universe and the nature of our cosmic surroundings. These interstellar travelers bear messages from distant realms, preserving information about stellar environments and planetary formation processes that unfolded during our galaxy's nascent stages, a time vastly different from its present state. The fleeting passage of ATLAS through our solar system represents a brief interlude across cosmic distances, connecting our planetary system with ancient stellar environments through the direct exchange of material. Comprehending these cosmic linkages offers perspective on the vast spatial and temporal scales that define our universe, while simultaneously highlighting the remarkable capacity of human scientific inquiry to decipher signals emanating from the cosmic abyss. These explorations will continue to broaden our cosmic perspective, revealing the intricate relationships between stellar systems and the overarching galactic environment we inhabit. The ensuing questions. While Atlas has yielded remarkable insights into interstellar objects and galactic evolution, it has also posed profound questions that will undoubtedly guide astronomical research for many years to come. The underlying mechanisms responsible for the anomalous characteristics observed in Atlas remain poorly understood, necessitating the development of novel theoretical frameworks and enhanced observational capabilities for their elucidation. These enigmas underscore existing lacunae in our comprehension of cometary physics and interstellar phenomena. The true range of diversity among interstellar objects is still unknown, with each new detection potentially revealing attributes that defy current theories and demand new explanations. Future surveys will determine whether Atlas represents a typical example or an exceptional anomaly. The frequency and properties of interstellar visitors offer valuable data regarding galactic structure and evolution, complementing other astronomical observations. However, interpreting this data requires a thorough understanding of complex dynamical and physical processes. The potential for detecting artificial objects among interstellar visitors raises profound questions about the prevalence of technologically advanced civilizations and our capacity to identify evidence of intelligence within astronomical data. These inquiries will stimulate ongoing research and technological advancements, driving progress in observational capabilities and theoretical understanding that benefit astronomy as a whole. A concluding reflection. As we have collectively navigated the latest discoveries concerning Atlas and unraveled the enigma of the so-called second comet, we have witnessed firsthand how a single cosmic visitor can profoundly alter our understanding of the universe around us. Whether you are drifting toward slumber as dawn breaks in Tokyo, finding solace in these words during London's quiet evening hours, or perhaps encountering this exploration during an afternoon respite in Sao Paulo, you have been part of something truly remarkable. The peculiar green hue of Atlas, captured during September's lunar eclipse, signifies more than a mere alteration in color. It encapsulates the dynamic nature of our cosmic environment, where ancient materials from distant star systems continue to evolve and unveil secrets as they interact with new surroundings. The sudden brightening that surprised astronomers, the enigmatic sunward radiance that defies conventional physics, and the exponential surge in cyanide production all point to processes that we are only beginning to grasp. The confusion surrounding the designation of a so-called second massive comet exemplifies how rapidly information can transform in our interconnected world. While Comet Bernard Danieli Bernstein is indeed colossal and approaching our inner solar system, its arrival is still years away, and it poses no threat. The viral narratives that conflated multiple celestial bodies serve as a reminder of the importance of meticulous, patient scientific investigation in an era of immediate information dissemination. As Atlas speeds toward its perihelion on October 30th, concealed from our Earth-based viewpoint by the sun's glare, spacecraft positioned throughout our solar system will be privy to its most dramatic moments. These robotic observers will acquire data that is inaccessible from Earth, adding crucial pieces to the puzzle of this cosmic messenger's true identity. What resonates most profoundly with me about Atlas is its embodiment of our galaxy's interconnectedness. This ancient wanderer carries chemical imprints from stellar environments that existed when our cosmos was young, traversing millions or perhaps billions of years through the void between stars before briefly illuminating our corner of space. In studying this visitor, we are engaging in a form of galactic archaeology, deciphering messages etched in ice and rock by distant suns. Tonight, as you prepare for rest, consider that somewhere beyond our atmosphere, telescopes are diligently tracking this extraterrestrial visitor as it hurtles towards its rendezvous with our sun. In the coming weeks, as Atlas emerges from solar conjunction and commences its lengthy voyage back into interstellar space, it will carry with it vestiges of our solar system's unique signature, potentially seeding distant regions of our galaxy with particles that once danced within Earth's magnetosphere. The questions prompted by Atlas will undoubtedly persist long after its brief transit through our cosmic vicinity. Each unusual characteristic challenges our current understanding and pushes the boundaries of theoretical physics. As we anticipate the arrival of the next interstellar object, we can be confident that it too will surprise us, unveiling novel aspects of the cosmic environment that we are only just beginning to explore. Until we next meet beneath these nocturnal skies, continue to gaze upward, persist in your inquiries, and remember that you are an integral part of a universe far more extraordinary and wondrous than we ever dared to imagine. Sweet dreams, fellow cosmic voyagers. If tonight's exploration has ignited your curiosity regarding the ongoing mysteries surrounding Atlas, I encourage you to share your thoughts in the comments section below. Which aspect of this interstellar visitor do you find most intriguing? Are you planning to observe the comet's reappearance from solar conjunction in November? Your engagement contributes to the cultivation of a community of midnight science enthusiasts who find wonder in the cosmos. Do not forget to subscribe for further in-depth explorations of the universe's most captivating enigmas. And activate that notification bell so you will be among the first to be informed when new discoveries emerge from the cosmic depths. The universe is vast, replete with secrets awaiting discovery. And together, we shall persist in unraveling them, one gentle night at a time.